for this question, once again, let's pick a representative slab from the region. Okay. So first thing we're going to do is find the work required to put that slab into position, to lift that one up to 1 foot above the surface. So work equals force times distance. The force to lift that slab equals to the weight of the slab, and the weight is volume times density. Density 62.4. I'm going to worry about distance in just a little bit. How about the volume of the slab? Pi x squared times, the radius is x. Again, this is very important. It's not a constant of 8, right? Because only the biggest disk within this hemispherical container has a radius of 8. As you go further up, the radius is not 8. It keeps changing, and we call that radius x in general to represent the change. So because it can change. Okay, so pi x squared times 62.4. And the thickness of the shell or the slab is delta y. Right? So when you find the volume of that slab, it's pi x squared times the thickness, which is delta y. And then the distance it has to be carried. How far will that slab have to be carried? Exactly, this distance, which is 9 minus y. The distance is 9 minus y, and I'm replacing it as such. Once again, we have a dilemma. We have an x squared with an expression where you have a delta y. Delta y tells me I'm going to keep dy, or the y variable in the equality, in the integration. I need to get rid of that x squared there. Can I use similar triangle ratios? No, that was for the cone. But for this problem, we know the equation of the circle. And what is the equation of that circle? X squared plus y squared equals 8 squared, or 64, right? Okay. So from there, what can I get for x squared? 64 minus y squared, right? That's what I need to replace in my equation to get rid of the x and write it in terms of y. Any questions about what I did there? Again, because this slab is bordering that circle on the edge, that means no matter what that radius is, to get the y at that point, because that point is along that circle with x squared plus y squared equals 64, you can use the fact that x squared equals 64 minus y squared. So that means instead of x squared, I can put just that. Still have my constants to deal with, still the delta y and still the 9 minus y. Okay? And to find the total work done, what should I be doing now? Integrate the above, right? That's just for one slab. You want to find for total, for all the slabs, total work done to pump this container, the contents up to y equals 9 level. So let me begin by putting all the constants up front. Inside the integral sign, I have 64 minus y squared times 9 minus y. And the limits of integration are, let me hear some suggestions from you guys. What will be the limits of integration here? I think there's two possible options, right? 0 to 9 or 0 to 8. Which one is the correct one? Think of it this way. You're writing one of these quantities, delta W, for each slab, and then you're adding them up. The slabs physically go from where to where? The actual slabs come from the actual physical water that is in the container, and they go from where to where? They go from 0 to 8. Again, you're writing basically one delta W for each slab. The lowest slab is at the y equals 0 level. The next one is like a little bit higher, a little bit higher. The last slab ends at y equals 8. So when you're adding it up, you're adding it up for all the slabs that had to be moved. And so that addition should be from 0 to 8. That's what the integral is going to do for us. It's going to total all the work done for all the slabs. Okay, so Okay, the distance we're carrying is 0 to 9, but the actual water that exists is from 0 to 8. So the slabs come from the actual water, and they extend from 0 to 8. Again, we wrote one delta W for each slab in the container, and those slabs are only in existence from 0 to 8 level. That's why we're going from 0 to 8. Okay, how do we finish this question? How do we integrate something like this? FOIL it out, exactly. FOIL it out and then integrate piece by piece. So let's just integrate this. And then plug in the limits. Okay, I know some of you may have already done this. If so, please let me know what you're getting. 401,480 foot-pounds. Okay, and finally, I want to go back to that example that we're talking about, sending a satellite into space. You know, how much work would be required. That's a little bit different than these container examples, filling in and filling out. As a matter of fact, I'm going to go over the example that your textbook has in that section. I'll just go over that with you. So if you like, open to that page in your textbooks. Under the work section, I believe it is on page 490. Page 490 from your textbook. Again, I'll also open it up here for your convenience. Let's see. $490, I believe. Page 490. So there's a problem. Let me give you a moment to read the question first. So the question is asking how much work is done in propelling this module to a height of 800 miles above the Earth. And again, it's given that the radius of the Earth is 4,000 miles. And it's also given that the space module weighs 15 metric tons on the surface of the Earth. Now, these questions are a little bit different, and they make one assumption. And the assumption is the following, that basically the weight of an object varies inversely with the distance from the Earth. Actually, varies with square of the inverse. So the further away you go, away from the Earth, the lighter the object will basically feel. So the force is a constant divided by x squared. Again, the further away you go, x being the distance from the surface of the Earth. Okay. First thing we're going to do is, and this will be given to you as F equals C over x squared. First thing we're going to do is we're going to determine the constant C. Okay. So we're going to use the given information. They said on the surface of the Earth, the space module weighs 15 metric tons. So we're given that on the surface of the Earth, it's equal to 15. The constant we don't know. But on the surface of the Earth, x, which actually is the distance from the radius of the Earth, is 4,000. So on the surface of the Earth, we're using 4,000 for x. And from this information, we can gather what that c is, the constant for this space module. So C equals 15 times 4,000 squared. Can you tell us what that is? What do we get? 240 million. 6 zeros at the end there. Okay. So that's the constant C. And to find the total work done, we're going to go to the first formula that we had seen. The total work done will be force times distance. And force is the force given right here. Force is the constant over x squared. And now we know what the constant is, except I'm going to put C for now because I don't want to write that long number over and over. At the moment, just assume that we know that what C is 240 million. So we're going to integrate C over x squared dx. And the question is, from where to where are we going to integrate this? So we're trying to find the total work done when it goes from this point to this point, right? So all the distances here are taken from the center of the Earth. So which two limits would you then put for the limits of integration? For x equals we're going from the surface of the Earth to 800 miles above the surface of the Earth. So what limits of integration would you use here? Again, all the distances are taken from the center. So like when you're here, you x equals 4,000. And what will be the upper limit of integration? 4,800. 4,000 to 4,800. Now, how do we integrate this? A constant over x squared. What is the integral of that? Think of c times x to the negative 2. You add 1 to the power, you divide by the new power, right? You're going to end up with c times x to the negative 1 over negative 1. In other words, you're going to end up with negative c over x, going from 4,000 to 4,800. Okay. And we know what c is, right? C was 240 million. And x is going to be 4,000 to 4,800. Go ahead and plug in 4,800 first. What is 240 million divided by 4,800? And because of the negative we have, it should be negative 50,000 minus another negative. This time plug in a 4,000 for x. And let's see what we're getting there. Plug in a 4,000 for x. What is 240 million divided by 4,000? 60,000, and the two negatives will give us a positive there. So we have 60,000 minus 50,000, a total of 10,000. The units are not going to be foot-pounds here because the distances were not measured in feet and the weight was not measured in pounds. What were they instead? Let's go back to the question. Instead of foot-pounds, what are we going to have? Instead of feet, we have miles, right? Miles. And instead of pounds, we have tons or metric tons, so mile tons. And it is possible to convert the answer to foot-pounds, but at the moment, we're just going to leave it like that. 10,000 mile tons would be the energy required to propel this satellite into space. Okay. And I would like for you to add the following question to your homework, because I don't know if I had one about, about satellites like the one I just did. Please add number 17. It may have already been assigned, and if not, please add it to your homework questions as another example. As a matter of fact, add this to the bottom of your group activity. So I want to see this question also solved with all the other group activity questions that you have in this section. Okay. Next, we will take a look at a spring mass system. It looks like I'm going to have to change the battery on my microphone first. Just a moment, please. I'll be right back. All right, fresh batteries, ready to go. So we'll take a look at another example from the work section. This one is about a spring mass system. For the spring mass systems, we need to be familiar with a formula called the Hooke's law, and which states that for a spring mass system, force equals K times X. Now, X is the amount of stretch or compression, the stretching or the compression of the string, and force is the force required to be able to sustain a compression or stretching of X units. Again, X is the unit of length, of course. So force equals K times X. And for this question, a force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. So for spring mass problems, basically the typical problem will be like this. Work equals the integral of force times distance. In this case, force is for a spring mass problem K times X by Hooke's law dx. So our job is mainly to determine what K is and also to determine the limits of integration. In this case, because they said compressing the string additional 3 inches. So it was already compressed 3 inches. So we're going to go from 3 to 6 to find the total force required or the total work required to accomplish this job, to compress the string from 3 inches to 6 inches total. So first we need to find what K is, and there's some information that you can use to obtain that, that constant K, like 750 pounds compresses a spring of 3 inches. It says compresses a spring 3 inches from its natural length of 15 inches. We really don't care that much about what the original length was. The main thing that we care about is how much that spring was compressed when that force was applied. So in this case, 750, the force equals K times X, and 750 pounds provided a compression of 3 inches. So K equals 750 over 3, or 250. So now we can come back over here to find work, integrate from 3 to 6, force, which is Kx, which in our case is 250 times X dx. And if we integrate this, we're getting 250x squared over 2, going from 3 to 6, and that is 125x squared going from 3 to 6. And if we simplify it, we get 125 times 36 minus 9, or 125 times 27. So the final answer should be 3,375. And notice we did not use feet, we use inches, so our answer will be in terms of inch pounds. So we have 3,375 inch pounds. So I suppose we could divide this answer by 12 to find also the corresponding foot pounds if there need be. In this case, everything was in inches. I'll just keep the answer in inch pounds as well. Another spring mass problem. This time a little bit different units. Instead of the foot-pound system, we have meters and newtons, but the idea is the same. A spring has a natural length of 1 meter. A force of 24 newtons stretches the spring to a length of 1.8. So the net amount that the spring was stretched is 0.8 meters. So if we use force equals K times X, remember X represents the amount of stretching or compression. And so 24 newtons equals K times the amount of stretch, which would be 0.8 meters. So K equals 24 divided by 0.8, or we can write it as 24 over 8 over 10. In other words, 240 over 8, or 30. Now that we know what K is, to find the total work done, once again, we need to find the integral of force times distance. And again, think about why for these questions we're using an integral process. Because when you have a spring that you're stretching, the first amount that you stretch is that you don't have to apply such a huge force. The further away you stretch, the next inch, the next meter in this case, the more you stretch, the more force you have to apply. But the force you have to apply to go from here to here is not the same as the force you have to apply from here to here, etc. In the beginning, you have to apply less force, and you have to periodically apply more. So it's a variable force. So to find the total work done while you're applying the variable force, we need to do the integration process. Okay, so the total stretching. So we already found the constant K, and the part B was asking how much work will it take to stretch the spring 2 meters beyond its natural length. So to go from 0 stretching, and again, the limits are usually set in terms of how far you're stretching your spring or compressing it. In this case, to go from its natural length, which is 0 compression or 0 stretching, to 2 meters. So we'll integrate 0 to 2 of f of x dx, and in this case, the function is k times x dx. So here we get 15x squared going from 0 to 2, and that gives us 60. And as to the units, we had newtons and meters. So instead of foot-pounds, we're going to actually end up with another unit of measurement called Newton meters. And this has another name. In your physics classes, you might also see this as joules, or just abbreviated J. So 60 Newton meters or 60 joules is the total work done to stretch the spring from 0, from its original position, to 2 meters beyond its natural length. And finally, there's one last thing I want to point out to you, and that is another example from our textbook. It is a spherical container. There. Again, this is also an example from this particular chapter, the work chapter in our textbook. I'm referring to the Larson book. Of course, we may be using a different book at the time you're viewing this, but if we have the Larson textbook, you may be able to find this one from our text. The reason I want to show you this example is because of the way of selection, the way they have selected the coordinate system. First, let's read the question. A spherical tank of radius 8 feet is half full of oil that weighs 50 pounds per cubic foot. Find the work required to pump oil out through a hole in the top of the tank. Okay, the first scenario is the way that the book has placed, which is they have placed the x-axis at the bottom of the sphere. So remember, the radius is 8, so you notice they put 16 up here. So they have placed the x-axis at the bottom of the sphere. So what will then be the equation of the circle? Now it has been shifted along the y direction by 8 units, right? The radius has been shifted. The radius is at the point 0, 8. Therefore, the equation will be x squared plus, remember that general rule, which is x minus h quantity squared plus y minus k quantity squared? This will be y minus k, where k is 8. The radius has been shifted 8 units upwards, so that's why we have y minus h squared equals the radius squared, which will be 64. Okay, all I want to do is set this problem up, and I also want to show you how you can set this question with a different positioning of the coordinate system, namely by placing the x-axis at the center of the sphere, not at the bottom of the sphere. Okay, for this question, first of all, the tank is half full, and instead of our typical 62.4, we have 50 pounds per cubic feet or cubic foot for the oil's density. So you would do everything as you would normally do to find the total work done. First, you find the work done for one slab, which is pi x squared. You would pick one slab from this region. Again, the thickness will be delta y, so we'll have a dy in this integral. What we want is force times distance. Force equals to the weight, which is volume times density. The volume of that slab equals pi times x squared times delta y, which I replace it by dy, times the density, which is 50. So now we have the weight of the slab. And about the distance that this has to be carried based on this given coordinate system, notice that we are pumping the oil to the top of the tank. So this slab will have to go a distance of 16 minus y units. And because it's only half full, the limits of integration will be from 0 to 8. The only problem here is the x squared. So to replace the x squared, basically I need to come back to this equation on the top and solve for x squared in there. So x squared equals 64 minus quantity y minus 8 squared, which of course we could simplify further. Again, all of that for x squared. And then times 16 minus y. Okay, let me double check all of that. All right, that looks good. So that's one way to set up this problem. Okay. And here is another way. I want you to see this because usually I would ask you to set it up in a way that would make it easiest for you. Like, for example, in this case, you have to spend a lot of time simplifying this integral at the end here. Another way would have been to put your sphere where the center is at 0, 0. Then the equation of this sphere is going to be simply, or the surrounding circle, I should say, would be x squared plus y squared equals 8 squared. It has not been shifted, so h comma k are 0 comma 0 values. So once again, it's half full. Take a slab from the region. So the beginning part is not going to change. That is total work equals 50 times, that's the density. The volume of the slab is pi x squared. The distance that it has to be carried, since we're emptying it to the top of the container, now the top is at y equals to 8 level. So it's going to be 8 minus y. And since it's half full, we're going from here to here in terms of how many slabs we have originally. The slabs originally are from -8 to 0. And once again, thickness of the slab was dy. And finally, we just need to replace x squared. And let me factor out the constants. -8 to 0. Instead of x squared, I can use this equation, which is 64 minus y squared times 8 minus y dy. Okay, let me double check. Okay, it looks good. So basically what I'm saying is you can either evaluate this integral or you can evaluate the previous integral. But either way you do it, it will still be the same final answer. So choose the one that makes the layout of the problem easier, the integration easier for you. Like on the first one, you had to do a little bit complication. You had to remember that this one has been shifted 8 units up. So you had to go with the updated equation of a circle. If you put it directly at 0, 0, then you have to deal with somewhat negative quantities in your setting up of the integral, but then you're dealing with an easier version of a circle, one where h and k are 0, 0. I just also want to go over one more explanation about this 8 minus y. That's the distance, because this slab has to be carried this distance. And for example, imagine this point being y equals to -1, let's say. So if you go 8 minus y, you would have 8 minus -1, and indeed that formula really works even when the slabs are in the negative region. So 8 minus -1 is 9. Indeed, the slab is 9 units away from the top. So 8 minus y is an expression that will describe the distance that each slab has to be carried all the way to y equals to 8 level. And whether the slab's on the top or on the bottom, that same expression will work. Finally, I had them both on the same page for your convenience, and there they are. If you evaluate them, you will find they both give the same final answer.